In this lesson, we're going to look at derivatives in such a way that they'll be as useful for us as derivatives were in Calculus 1. So we'll be looking at directional derivatives and gradient vectors. Thank you. Thank you very much. Thank you. Thank you. So first of all, let's talk about what's called the gradient vector. If the partial derivatives of a function are defined at a point p, x sub 0, y sub 0, in the domain of f, then the gradient of f, or you could call it the gradient vector of f, or you could call it del f, and here's the notation for that. It's just the partial derivative of the function with respect to x times I plus the partial derivative with respect to y times j. And that is the gradient vector. Okay, what good is a gradient vector? Well, at a particular point, when you evaluate it at a particular point, it points in the direction where the surface is growing the fastest. And the opposite of this direction would be where it is getting smaller the fastest. Okay? That's a crucial point. Like, what is a gradient vector? It's a vector that on the surface at a point points where the surface is steepest, if you want. If you're on the side of the mountain, you're pointing at the peak. Of course, in the opposite direction of that, you're going down into the valley. So now that we know what a gradient is, what is a directional derivative? Well, the directional, just like the derivative is the slope of a tangent line, and I think everyone understands that, and you even got, I think, from previous lessons, that a partial derivative is the slope of the surface's intersection with a plane, which is like a line or a function in a plane. It's the slope of that line or that intersection of the surface and the plane, and that's understandable. But now we're going to make this even better. We're going to say we can find the slope of the surface in any given direction, and that's called the directional derivative, right? So let z equals f of xy be a surface in r to the third, in r cubed, and let p be a point in the domain of f. So that means there's a point x0, y0, and f of x, y0 that will be on that surface. Further, let u equal cosine theta I plus sine theta j. Okay? Now be a unit vector in the xy plane. Now what this unit vector u is doing is giving us a direction. So this is saying pointing in what direction. If you want to point due north, then let theta be pi over 2. See? If you want to point due east, let theta be 0. If you want to point due west, let theta be pi. See? And then you have a unit vector pointing in a certain direction. It describes the direction from the origin, of course, just like we always do with angles theta in standard position. Anyway, then the directional derivative of f, which is a number, is the dot product, and here it is. It's the dot product. This means the directional derivative in the direction of u of f at the point p, and it's del f, the gradient of f, dotted with our unit vector u. Think about what it really is. It's the length of the projection of the gradient vector onto the direction vector. Okay, recalling that the projection of del f onto u would be del f dot u over the length of u squared times, that's a times, not a dot there, times u. So this is just a scalar multiple of u. But now, this simplifies a whole lot. What is the length of u? Well, if it's a unit vector, it's 1. So you square it, you still get 1. And so, therefore, the length of this vector is just this dot product times the length of u, but what's the length of u? Well, that's 1, so that clears that up. Okay, now meanwhile, find the derivative in the direction of this vector, u cosine pi over 4i plus sine pi over 4i. In other words, in a 45-degree angle from the positive x-axis, what is the slope of this curve? And the curve is f of xy equals y minus x squared. And we're going to find it at the point where x is negative 1 and y is 0. So we're going to find the gradient vector of this curve, evaluated at the point negative 1, 0, find the dot product of that with this vector, and that will give us a number, and that number will be the slope of the curve, or sorry, slope of the surface, I should say, at that point in this direction. Okay, so f of xy, that's easy enough. F sub x, that's the derivative, partial derivative with respect to x of this, is negative 2x, and the partial derivative with respect to y is just 1. So that's pretty easy. And if we evaluate this partial derivative at the point where x is negative 1, y is 0, we get 2. And if we evaluate it, well, it doesn't matter where we evaluate it, the partial of y is going to be 1. So what does that mean? That means to find this number, okay, we would dot 2i plus j, see why it's 2i, plus 1j, with square root of 2 over 2i plus square root of 2 over 2j. I hope you know where that came from. What's cosine of pi over 4? Square root of 2 over 2. So when we dot these two vectors together, we get 2 times square root of 2 over 2, which is just square root of 2, plus 1 times square root of 2 over 2. So we get square root of 2 plus square root of 2 over 2. Well, that's 2 square roots of 2 over 2, so that ultimately gives us 3 square roots of 2 over 2. And that would be the slope of this surface at this point in this direction. Okay? Here's a picture. I'm going to try to show that. At the point where x is 0, that's here, and y is negative 1, that's here. And we want to point in a direction. Remember, this is the x-axis here, so we want to point 45 degrees would be pointing like in this direction. So we're finding the slope here pointing this way, 45 degrees, right, from the positive x-axis. Maybe as hard as it's going to be for me. Here's x and y in the normal sense that you're used to, and we're going to be at the point x is 0, y is negative 1, so that's about here, and we're pointing, sorry, I think I might have pointed in the wrong direction. I had to get it like this so I could understand. We're going to go this way. Pi over 4 is the angle. So the slope of at this point, the slope of the curve in this direction is 3 square roots of 2 over 2. Now here's another picture. I can't rotate this one because I had to capture it and put some more things on it, if you can see it. There's the point. There's that 3 square roots of 2. Pay no attention to the fact that it doesn't look like 3 square roots of 2, but keep in mind what the scale on the z-axis is. Scale on the z-axis is much higher than the scale on the x and the y. So, and this purple vector, of course the place I should put it is up here, but the purple vector, what is that purple vector? Oh, that's the gradient, right? And here's the unit vector in that direction. So the projection of the purple vector on the unit vector is 3 square roots of 2. So the points noted, by the way, this is incorrect. X is negative 1, y is 0 in the xy plane. That's not in the xy plane. That's in the plane where z equals negative 30. So my fault about that. Let me fix that. In the plane z equals -30, and x is -1, y is 0, and z is -1. I don't think that's true. On the surface, well, it might be on the surface, that's true. And if x and y are, as stated, on the surface, y minus x squared would be 0 minus 1, so it is on the surface. The slope of the line segment tangent to the surface here is 3 square roots of 2 over 2, and this is the directional derivative at that point in the direction of our unit vector u, and I think that's the little black one I drew in here, okay? So the gradient there is 2i plus j. Of course, now you can see this is the 2i plus j, and it's drawn in purple, and I hope that clears it all up. Below is a contour plot with the gradient vector at the point -1, 0, and pointing in the direction of steepest ascent, 2i plus j. That's the gradient vector there, 2i plus j, and it's pointing where the curve is steepest at that particular point. And so I did my best to draw that in there. And I want you to notice that it's at that particular point, the gradient vector is orthogonal to the level curve. Pretty cool. That's one of the properties of a directional derivative.